Okay, this is a video about differentiation with the power rule. Essentially, it's really a sort of a first step in calculus. It's something that is useful if with certain IGCSE courses, but also in A level if you need some calculus in order to be able to do some elements of mechanics, kinematics, for instance. Then it's a sort of a there's enough in it to actually get you going in that area. Okay, so all right, so it's introduction, if you like, to the first steps in calculus. What are we talking about? Well, let's ask this question. What do we mean by the gradient of a curve? Good question. We've got a straight line here. This red line is a straight line. We know what we mean by the gradient of that. We could describe this like y equals mx plus c, and m would be the gradient. We've done straight line graphs, I'm sure. And what we're doing really is we're measuring the rise over the run. So we could draw this and find this ratio of the rise over the run. And of course, it's the same wherever we draw this little triangle here. It's the same all the way along the line. The gradient is in fact constant for a straight line. But what about a curve? I mean, the gradient actually it varies as we go along. I mean, at this point down here, it's going to be relatively shallow. Up here, it's much steeper. Here, it's going to be negative. Okay, and the other thing is, how do we measure it? Because, of course, if we take how do we draw a triangle? Because if we draw this sort of triangle around here, for instance, well, the top of it's going to be steeper than at the bottom. So what exactly do we mean? I think to get to this, what we have to do is think about what happens when we zoom in. No, I've already said the value of the gradient is going to depend on the value of x. So if we zoom in on that value of x, here it would be value of x would be 10, wouldn't it? So if we zoom in closer and closer and closer, what we're actually doing is we're actually find that we get really zoomed in and effectively got a straight line. And that is what we are measuring. A bit more difficult, really, a bit difficult to do graphically, certainly, because we'd have to be drawing a very, very small triangle, wouldn't we, to try and understand the rise over the run. Well, another way of thinking about it, of course, is by the time you get to that, we're actually looking at the tangent at that point as well. So just hold that thought. So the gradient of an infinitesimally small section of the curve, when we've zoomed in at this point, x equals a, and that is actually the gradient of the tangent. So what we're looking at really is the ratio of something which is a very small change in y as we go along, from along the x-axis, if you like, as the value of x increases. So a small change in y compared to a small change in x. It's that ratio. And we sometimes describe that by the delta of y to the delta of x, delta being the Greek letter delta. And that's often used, but more commonly, we actually change that delta to a d. So, and we write dy dx. And so what this means is a small change in y to a small change in x. And this is a ratio. And you'll see in calculus that actually handling these as a ratio actually helps to clarify quite a few things. Okay, so that is sort of what we're talking about. Now, the next thing really we want to think about is the power rule, because this is fundamental really when we're dealing with functions that are polynomials, algebraic functions, we might say. And quite simply, if we've got a function which is y equals 5x cubed, for instance, so if you imagine the graph of that, then the gradient would be 15x squared. Now, how have we got that? What we've done is we've applied this power rule, and the power rule is that we multiply the coefficient, which is 5, by the power to get the new coefficient. That's 15, and then we subtract 1 from the power, giving us, in this case, x squared. So the gradient is 15x squared. So this is a function, of course. This 15x squared is a derived function. It's derived from the original function. It's called a derivative, and the process by which we get it is called differentiation. And as I just said, the derivative itself is a function. This thing. Okay, so that is the power rule essentially. Something which is not really a power rule, but it's just true of in calculus. The derivative of a sum of terms is the sum of the derivative. So if we've got a function like this, y equals 5x cubed plus 3x squared plus 2x plus 5, then if we go through our differentiation process and we apply that power rule, so we've got 15x squared just as above, and here we've got 2 times 3, subtract 1 from the 2, giving us 6x. 2x, well, that's really 2x to the power of 1, I suppose, isn't it? So 1 times 2 would be 2, and then x to the power of 1, subtract 1 from that, so it's x to the power of 0. X to the power of 0 is 1, so this 2x just becomes 2. And also, the 5, of course, we could think of it as being 5 times x to the power of 0, x to the power of 0 being 1. And then, of course, if we multiply the power 0 by 5, then that term is just going to drop out. So this would be the derivative, the derived function. Now, interestingly, and this is not something which will worry you too much until you get to sort of a kind of slightly more further on in the process. The power rule can be used even if the power is not a whole number. So y equals x to the power minus 3 over 2, then the derivative, which represents the gradient, is this. You see what we've done, minus 3 over 2 times the coefficient of 1. And then subtract 1 from the minus 3 over 2, giving us minus 5 over 2. So so that is worth knowing. Let's just move on and see 1 or 2 other things. Well, why do we do it? Well, actually, the ability to find the gradient at some point means that there's a lot of problems in maths that we can solve. And most importantly, I think, knowing the value of x, always talks about x, but it's just a letter. Very often our functions will be a function of t, in mechanics, in lots of applied maths, particularly mechanics. Then we might be actually interested in the independent variable being time. But at the end of the day, it's just a letter, and the process is exactly the same. But knowing the value of x when the gradient is 0 is often important in solving optimization problems and all sorts of problems, basically. Now, when we think of terms in terms of a function notation, we would write this: f of x equals 5x cubed, for instance. Then the derivative could then be df dx, and we're just using f instead of y, really, aren't we? But more commonly, if we're sort of using this kind of notation, then we would refer to the derivative as f prime x, like that. Okay, so it's another bit of notation just to bear in mind. The other thing, really, which we don't have to delve into now, and this is really certainly A level, but it's kind of worth just having a brief glimpse at it, I think, is why does this power rule work at all? Well, we have a process. It's called differentiation from first principles. You will cover this. This graph, for instance, is this line is x divided by 2 all squared. So the process that we go through really is we do draw this. We do draw our little rise over run triangle. And if you can imagine this, this is the point x. So this is the general point. And this, we just draw it with a distance h here. So this here, where this top black dot is the function evaluated at x plus h, because this point here is x plus h. And this is the function evaluated at x. So the rise is going to be this, the run is going to be this, and then what we have to do is, well, we evaluate this, but we don't evaluate it necessarily in a traditional sense, because in this case, for instance, we'd be dividing, you know, when h is infinitesimally small, then h is in effect 0, so it can't divide by 0. So what we have to do is we have to look at where this ratio is tending to as h gets smaller and smaller and smaller. So, but that's a whole new different topic which we don't have to cover here, but I think it's perhaps just worth being aware that this is the sort of analysis that we're often doing, and we can prove a lot of differentiation rules, including the power rule, this particular way. So I'll look at a few examples. Okay, quite simply, here we got a function 5x squared minus 3x plus 7. Find the value of dy dx when x equals 1. Okay, well, we'll just follow the power rule. 2 times 5 is 10. So 10x, and then minus 3, the 7, as I say, will just as a constant, just disappears. And then we're going to evaluate that when x equals 1. So we're using this notation here, this line down with 1 there. That means we're just evaluating it at 1. And that's going to give us 10 times 1 minus 3, 7. So that's it. Number 11, you might see this. Don't be confused by this. We can just multiply this out. 2x squared minus 7x plus 3, and then just apply the power rule, just as we have done before. 2 times 2 is 4, and 1 times 7 is 7. So that is that example. Now here's another example, which is a little bit more to it. Well, not much more to the differentiation, to be honest, but it's just a little bit more complicated problem to solve. So we've got a function here. We don't know what p is. P is unknown. It's a constant. The value of dy dx when x equals 3 is 5 times the value of dy dx when x equals 1. Work out the value of p. Okay, now this statement here, I've just copied it down here, is basically it's an equation, but it's an equation not written in maths terms. It's written in more sort of narrative form, isn't it? The value of dy dx when x equals 3, that's that, is, what's your equals, 5 times the value of dy dx when x equals minus 1. Is that okay? So that is your that's your equation. That's written in mathematical terms as opposed to narrative terms. And then a lot of these problems, you know, it's quite important just to be able to spot the equation in narrative terms, so you can then use it like this. Now, yeah, we can work out these things. Dy dx when x equals, well, dy dx equals 8x plus p. All right, it's just derived from there. 2 times 4. So evaluated at 3, that's going to be 24 plus p, just substituting 3 in there. And again, minus 1 in there gives us minus 8 plus p. So we can actually substitute those into this equation. So 24 plus p equals 5 times minus 8 plus p. And that's going to give us 4p equals 64 and p equals 16. Okay, so in terms of the differentiation, that's no more complicated, is it? But we just have a, you know, an unknown constant in there. Let's go on. Right. Okay. So this is the idea of turning points, or sometimes called stationary points. Those two terms seem to be used equally. They mean the same thing. Let's just have a look at this concept. So if the value of a function changes from negative to positive as x increases, so as we sort of travel along, the x values are our function value, y value, if we're calling it that. In this case, goes from negative to positive. So it's going from bottom left to top right, isn't it? So then the gradient is positive. You can see that positive gradient there. Right, so let's just take this a stage further. If the value of the gradient function changes from negative to positive, that's what we've got here with this curve. Got a negative gradient down there. Obviously, it's changing in terms of its value, but it is negative all the way here, and it's positive here. So if the value of the gradient function changes from negative to positive, then the gradient of the gradient is positive. Okay, right. You might want to pause the video and get your brain around that, but just take that as it says. So therefore, if the derivative of the derivative is positive, then the turning point is a minimum. Right, now you don't have to worry too much about that, but I'll give you a little challenge just to think that one through for yourself. Okay, but we can see here, it is an example where we're going from negative gradient to positive gradient, and the turning point here, this point here, is a minimum. Okay, and you can see that if it was the other way around, we went from positive to negative, then we'll be talking about a maximum. So now this derivative of the derivative is called the second derivative, and we denote it by this thing d2y dx2, or if we're in kind of function notation speak, then we would use f double prime x. So as we said, if the second derivative evaluated at whatever point we're interested in is greater than 0, then the value of the function is a minimum at that point where x equals a. Okay, x equals 2 in this situation. Now, of course, some curves may have more than one turning point. The cubic, for instance, may well have a maximum and a minimum. You can imagine a cubic graph that may start from the bottom left, goes up, tops out, comes down again, bottoms out, goes back up again. Quartic, x to the power of 4 graphs are going to be even more complicated, and so on. Now, if you wanted a little thing to remember this, it's always worth going back to a simple example like y equals x squared. So the derivative would be 2x, okay? And the second derivative would be 2. Now, 2 is positive, and so therefore the turning point, which is the bottom of that graph, would be a minimum. And of course, y equals minus x squared would, you know, that would be a negative second derivative, and that is indeed a maximum because it represents a sort of upside down bulb. Right, so that's turning points and stationary points, and a really important sort of crucial concept in calculus. Let's have a look at an example which is kind of in that area. Find the coordinates of the stationary point on the curve y equals x to the power of 4 plus 32x. Okay. So the gradient is this function here, just following the differentiation process. Now we know at the stationary point, the gradients are 0 because that's where it bottoms out. Yeah, okay. So if we were to do our rise over run at that very, very small point, we would get 0. In fact, the gradients, it's the point where gradient changes from negative to positive or positive to negative. Typically, not always. So we can just solve that then. So that dy dx equals 0 equals this, and that's going to give us x equals 2. It does actually say the coordinates, so what I haven't done there is actually calculate y, so we would actually plug x equals 2 into there and get 16 plus 64, 80. Okay, so that is that. Then it says determine whether this stationary point is a maximum or minimum. Now, yeah, typically we would find the second derivative. And in this case, that means doing the derivative as well of this function, 12x squared, the 32 disappears. And then we're interested, of course, in the point where x equals 2. So we would have to evaluate that second derivative at x equals 2. So that's 12 times 2 squared equals 48. Now, the important point here is that that is positive. Second derivative is positive at x equals 2. So x equals 2 is a minimum. And then the last part of this question says, for what values of x does x to the power of 4 plus 32x increase as x increases? So it increases when the gradient is greater than 0, of course. Which means that this, being the gradient function, is greater than 0. Well, we can just solve this, and this is going to give us x is greater than -2. And here's a little bit of this curve that I've done. Thank you, Desmos. And it does, in fact, show that from -2 onwards, then the function is actually increasing. Okay, so that's a nice little example. Now here's one. Now, of course, we're going to apply the power rule, aren't we, for fractional powers here? So it didn't take us long to actually get to needing it. Curve C has equation y equals 12 times square root of x, or x to the power of half, we might say, minus x to the power of 3/2 minus 10. Use calculus to find the coordinates of the turning point on C. As I said, the terminology changes between stationary and turning, and they both mean the same thing. Y, so just rewriting that, y equals what I just said there, and then we go through our differentiation process to find the gradient function. Okay, so, half times 12, 6, and so on. And 3/2 is, a bit of a mistake there, 3/2 should be the coefficient of that. So that's messed up my calculation, but never mind, we just work that through. We'll assume that I put the right number in. Use calculus to find the coordinates of certain turning point, so we can work that through. We get the turning point dy dx is equal to 0, and then we can solve our equation and get out the x value. Now to find, it says find the second derivative, so we can just work that through again. Obviously, I've got slightly wrong there, but that's going to give us the second derivative. And if we evaluate that at 6, now we can kind of work all these numbers out, if you like. But I think once we've got to this point, what we can actually see is we've got something which is going to be positive. This is going to be 6 to the power of something, and 6 positive number to the power of anything is going to be positive, as is this. They both got negative coefficients, so this whole thing is going to be negative. Okay, so we don't always have to work through the second derivative. So don't necessarily just leap into actually doing the second derivative, even when a bit of intuition can actually give you the answer. But in this case, yeah, the second derivative is going to be negative, so the turning point is a maximum. Right. Okay, so that's interesting. Right, now optimization problems. Okay. Now these grade these problems. This one is kind of a nice little illustration. Let's have a look. The volume V of a box, height x centimeters, is given by this. It's cubic. Cubic, so the highest power on this would be x cubed. So find dv dx. Now we could draw this. And in fact, what I've done, again using Desmos, I've actually drawn this this graph here. And so v is the vertical axis. We've got x is the height, which is the independent variable along here. Now we are interested in between 0 and 5, and 0 and 5 are there and there, those 2 points there. So naturally, see what happens is that as we increase the height, I mean, we don't know what the shape of this box is. It could have a weird cross section. Don't really know, but anyway, any other problems, we might well have to work out this formula for ourselves. But here it's just given to us. Okay, so we can see that as we increase the height, then the volume increases up to a point. We don't know what the height is yet, and then decreases down to here when it's 0. I think we'd probably see from the function that this point is going to be x equals 5, and then it, you know, for bigger values, 6 for instance, it starts to go rise up again. But we're only interested in this bit between 0 and 5 here. So hence find the maximum volume of the box. Right, okay, so if we expand our function for v here into that and then do our differentiation process, we end up with this derivative here. And we know that at the turning point here, then at that point the gradient is sort of stuck between being positive and being negative, so therefore it's 0. So we can write our equation as the gradient is equal to this. We can solve that for x. Okay, so well, divided by 4. I've done an explosion in the middle, so if you're not familiar with that method for solving quadratics, then that'll be on another video. But that gives us a solution of x equals 5/3 or 5. Now we're told that it's less than 5, so we can not worry about the solution of 5, which of course is actually a minimum. But this is the one we're interested in, 5/3. So the actual maximum value of the volume is when x equals 5/3. So if we substitute that back into our original equation here, like this, then we can just work that through. It's not a whole number. It comes to 74.07 cubic centimeters to 2 decimal places. Okay, so now the third part says use calculus to justify that the volume you found in part B is a maximum. Well, it does say use calculus, so I think really we're going to go down the route of doing the second derivative, but we wouldn't necessarily have to do that if the question was didn't really require us to use calculus. The reason being that, well, we've got 2 solutions, and we know this is a positive cubic. The coefficient of x cubed is positive in this. Well, we can see from here. So we know it comes up from the left, goes up to a maximum, comes down to a minimum, back up again. Okay, so the lower value of x is going to be the maximum. And we know that because we're interested in 5/3 and not 5, then it's going to be a maximum. But anyway, it says use calculus. So if we do the second derivative, we simply get this. And then we evaluate that at 5/3. I might even put the vertical line in here, and 5/3. It's going to come out to -40, which is negative, and therefore at x equals 5/3, we have a maximum. Okay, so that is that. So that is a problem of optimization, and these come all over the place. More typically going to see this sort of thing at A level, but useful to know. Whatever. Okay, just the final thing really is, and one of the reasons for the video is that sometimes you want to be doing calculus in some applications, including mechanics, when you might not have actually started studying it, in pure maths. So in this case, as in a lot of sort of physical problems, you're probably looking at time as being the independent variable. And that's what we've got here. Particle moves in a straight line, and at a time t, it has velocity v, where v equals this function here. So you can imagine how this is working. So it's going to get faster and faster and faster, this particle. So the first part says find an expression for the acceleration of the particle. Now, what we need to know here is that actually acceleration is the rate of change of velocity, and so as such, it's therefore the derivative of the velocity function. Okay. Acceleration is equal to the rate of change of velocity with respect to time. And quite simply, following our differentiation process using the power rule, that's going to give us 6t minus 12. So that is the expression for the acceleration. Now this is time dependent, so the actual acceleration is increasing as time goes on in this particular example. And then when t equals 2, show that the acceleration of the particle is 0. Well, it's interesting because when time starts, when we start measuring this and time is 0, then actually our acceleration is -12. It's actually decelerating. So some particle is probably, I don't know, motorbike has actually driven past us as we're stood by the side of the road, but it's slowing down. It's slowing down coming to some traffic lights. But the traffic lights change, and then it accelerates, and the acceleration becomes positive. So we can see, I think, when the acceleration is 0, when a equals 0, 6t minus 12 equals 0. So t equals 2. We could write the acceleration evaluated at 2, which is an acceleration function. The acceleration evaluated at 2 is equal to 0. So that's the sort of thing that comes in quite a lot. And sort of in these problems, it's useful to know that the acceleration is the rate of change of velocity with time, but also the velocity itself is the rate of change of distance or displacement. We tend to talk about displacement being almost a very similar concept. Velocity is the rate of change of distance or displacement with time. So there is a second part to this question, which I've stripped away. But if we wanted to work out the displacement function, so that would be in terms of time, s expressed in terms of time. We really have to find the thing that which, when we differentiate it, gives us this. Okay. All right. So now that process is called integration, and it's obviously a massive topic which we're not going to cover here, but I think you can, with a little bit of guesswork, you can reverse the process, and we would get that the displacement is equal to t cubed minus 6t squared plus 6t, but plus a constant. Now remember that when we differentiate this, then this constant disappears. So when we go the other way and do the integration, we need to put it back in. So we would need a boundary condition or some way of actually finding out what this constant is for this to be a useful equation. But anyway, just throw that in, which gives you something else to think about. And really, that's as much as I'm going to cover. There's actually quite a lot of ground covered there. Hope that's been useful. And yeah, I'll see you next time.